In quantum computing, a qubit or quantum bit is a unit of quantum information, the quantum analog of the classical bit. A qubit is a two-state quantum mechanical system, such as the polarization of a single photon. Here the two states are vertical polarization and horizontal polarization. In a classical system, a bit would have to be in one state or the other. However, quantum mechanics allows the qubit to be in a superposition of both states at the same time, a property which is fundamental to quantum computing. Origin of the concept and name. The concept of the qubit was unknowingly introduced by Stephen Wiesner in 1983, in his proposal for quantum money, which he had tried to publish for over a decade. The coining of the term qubit is attributed to Benjamin Schumacher. In the acknowledgments of his paper, Schumacher states that the term qubit was invented in jest due to its phonological resemblance with an ancient unit of length called cubit. During a conversation with William Wouters, the paper describes a way of compressing states emitted by a quantum source of information so that they require fewer physical resources to store. This procedure is now known as Schumacher compression. Bit versus qubit. The bit is the basic unit of information. It is used to represent information by computers. Regardless of its physical realization, a bit has two possible states typically thought of as 0 and 1, but more generally, and according to applications, interpretable as true and false, night and day, or any other dichotomous choice. An analogy to this is a light switch. Its off position can be thought of as 0 and its on position as 1. A qubit has a few similarities to a classical bit, but is overall very different. There are two possible outcomes for the measurement of a qubit, usually 0 and 1, like a bit. The difference is that whereas the state of a bit is either 0 or 1, the state of a qubit can also be a superposition of both. It is possible to fully encode one bit in one qubit. However, a qubit can hold even more information, e.g., up to 2 bits using superdense coding. Representation. The two states in which a qubit may be measured are known as basis states. As is the tradition with any sort of quantum states, they are represented by Dirac or bracket notation. This means that the two computational basis states are conventionally written as an qubit states. A pure qubit state is a linear superposition of the basis states. This means that the qubit can be represented as a linear combination of n, where alpha and beta are probability amplitudes and can in general both be complex numbers. When we measure this qubit in the standard basis, the probability of outcome is and the probability of outcome is, because the absolute squares of the amplitudes equate to probabilities. It follows that alpha and beta must be constrained by the equation simply because this ensures you must measure either one state or the other. Block sphere. The possible states for a single qubit can be visualized using a block sphere. Represented on such a sphere, a classical bit could only be at the North Pole or the South Pole, in the locations where and are respectively. The rest of the surface of the sphere is inaccessible to a classical bit, but a pure qubit state can be represented by any point on the surface. For example, the pure qubit state would lie on the equator of the sphere, on the positive y-axis. The surface of the sphere is two-dimensional space, which represents the state space of the pure qubit states. This state space has two local degrees of freedom. It might at first sight seem that there should be 4 degrees of freedom, as alpha and beta are complex numbers with 2 degrees of freedom each. However, 1 degree of freedom is removed by the constraint. Another, the overall phase of the state, has no physically observable consequences, so we can arbitrarily choose alpha to be real, leaving just 2 degrees of freedom. It is possible to put the qubit in a mixed state, a statistical combination of different pure states. Mixed states can be represented by points inside the block sphere. A mixed qubit state has 3 degrees of freedom. The angles and, as well as the length are of the vector that represents the mixed state. Operations on pure qubit states. There are various kinds of physical operations that can be performed on pure qubit states. A quantum logic gate can operate on a qubit. Mathematically speaking, the qubit undergoes a unitary transformation. Unitary transformations correspond to rotations of the qubit vector in the block sphere. Standard basis measurement is an operation in which information is gained about the state of the qubit. The result of the measurement will be either with probability or with probability. Measurement of the state of the qubit alters the values of alpha and beta. For instance, if the result of the measurement is alpha is changed to 1 and beta is changed to 0. Note that a measurement of a qubit state entangled with another quantum system transforms a pure state into a mixed state. Entanglement. An important distinguishing feature between a qubit and a classical bit is that multiple qubits can exhibit quantum entanglement. Entanglement is a non-local property that allows a set of qubits to express higher correlation than is possible in classical systems. Take, for example, two entangled qubits in the Bell state. In this state, called an equal superposition, there are equal probabilities of measuring either or, as imagine that these two entangled qubits are separated, with one each given to Alice and Bob. Alice makes a measurement of her qubit, obtaining, with equal probabilities, either or. Because of the qubit's entanglement, Bob must now get exactly the same measurement as Alice, i.e., if she measures A, Bob must measure the same, as is the only state where Alice's qubit is A. Entanglement also allows multiple states to be acted on simultaneously, unlike classical bits that can only have one value at a time. Entanglement is a necessary ingredient of any quantum computation that cannot be done efficiently on a classical computer. Many of the successes of quantum computation and communication, such as quantum teleportation and superdense coding, make use of entanglement, suggesting that entanglement is a resource that is unique to quantum computation. Quantum register. A number of qubits taken together is a qubit register. Quantum computers perform calculations by manipulating qubits within a register. A qubit is a collection of 8 qubits. Variations of the qubit similar to the qubit. A qubit is a unit of quantum information in a 3-level quantum system. This is analogous to the unit of classical information trit. The term qubit is used to denote a unit of quantum information in a d-level quantum system. Physical representation. Any 2-level system can be used as a qubit. Multi-level systems can be used as well, if they possess 2 states that can be effectively decoupled from the rest. There are various proposals. Several physical implementations which approximate 2-level systems to various degrees were successfully realized. Similarly to a classical bit where the state of a transistor in a processor, the magnetization of a surface in a hard disk and the presence of current in a cable can all be used to represent bits in the same computer. An eventual quantum computer is likely to use various combinations of qubits in its design. The following is an incomplete list of physical implementations of qubits, and the choices of basis are by convention only. Qubit storage. In a paper entitled, Solid-State Quantum Memory Using the 31p Nuclear Spin, published in the October 23, 2008 issue of the journal Nature, a team of scientists from the UK and US reported the first relatively long and coherent transfer of a superposition state in an electron spin processing qubit to a nuclear spin memory qubit. This event can be considered the first relatively consistent quantum data storage, a vital step towards the development of quantum computing. Recently, a modification of similar systems has dramatically extended this time to 3 hours at very low temperatures and 39 minutes at room temperature.